All right, so here we have the first problem on the problem set. You notice that whenever we're given the problem, the first thing we should do is annotate to make sure we know what's going on. Realistically, the first sentence that we have is when hydrogen gas and oxygen gas are combined in a closed and sealed container and given an initial spark, water vapor will freely form. All this first sentence is telling us is that a reaction is occurring between hydrogen gas and oxygen gas. Keeping in mind, of course, that both hydrogen gas and oxygen gas are diatomic molecules. And when they combine, they form water vapor. Water vapor, water is always water, it's always H2O. Now, as we continue reading, it says how many liters of water vapor can be created from 5 liters of oxygen gas and 3 liters of hydrogen gas, assuming standard conditions apply. So that means standard temperature and pressure. So kind of getting all of our information into one place is going to help us move forward productively. So let's get together all of our information that we know about hydrogen gas. So for hydrogen gas, we know that we have 3 liters. I know it's being held at a pressure of 1 atmosphere. And I know it's being held at a temperature of 273 Kelvin. For my oxygen gas, I know that I have 5 liters. I know that the pressure is 1 atmosphere because that's standard pressure, and I know that it's at a temperature of 273 Kelvin because that's standard temperature. So we can look at all of this piece of information and try and figure out what's going on. So notice that the problem asks us about water vapor. That's what we're really concerned with. That's what we're trying to figure out. However, the only variables I have to do with hydrogen and oxygen gas. That's a cue to me, that's a trigger to me that we're going to need to write a reaction, and we're going to have to create a BCA table to fulfill a lot of the requirements. However, with a BCA table, the only thing that ever goes into them is moles and mole values only. So looking at our piece of information, we're going to need to figure out the moles of hydrogen and the moles of oxygen in order to make that work. So now we have to look at our variables given and see if we can get to moles from what we're given. So you notice in the problem for hydrogen, we're given a volume, we're given a pressure, and we're given a temperature. If we consider for a second the ideal gas law, notice that in the ideal gas law, it involves a pressure, a volume, temperature, and the number of moles. R is that constant value of 0.0821. So looking at the information provided for hydrogen, we have a volume, we have a pressure, and we have a temperature. The only piece of information we're missing is the number of moles. So we can find the number of moles and then plug that into a BCA table to kind of move forward. From the previous page, we can remember, or we wrote down that the pressure for our hydrogen gas was 1 atmosphere. We know that it says that we have 3 liters worth of that gas, so that's our volume. We're looking for the number of moles. That was the whole reason we wanted to use the ideal gas law in the first place. We know that R has a constant value of 0.0821 atmosphere liters over mole Kelvin. Remember, this is just the unit for that number. It's like feet or miles. It's just a descriptor as to what that number is, like what it means to us. We also know from the previous page that it's being held at standard temperature, which is 273 Kelvin. Now, mathematically, we're going to do any of the math that we can do right away. So looking at the left side, I can take 1 and I can multiply by 3. So that gives us 3, and whatever we do to our numbers, we have to do to our units. So we took 3 and multiply by 1, that means we have to take liters and multiply by atmospheres. In the same manner also, we're going to look and see what we can do on the right-hand side. So we can take our temperature, 273, and multiply by R. Here notice that I'm going to have Kelvin on the top of that multiplication. I have Kelvin on the bottom of that multiplication. So that unit goes away, and we're going to be left with just atmosphere, liter over mole. So when I take 0.0821 and multiply by 273, I get a value of 22.4133. And remember, Kelvin on the top, Kelvin on the bottom, those are going to go away, and I'm left with just atmosphere times liter over moles. Now we have to solve for that n value. So I'm going to divide both sides by that 22.4133 value. And we're going to carry our units with us because it's going to make sure that our units come out correct at the end. So now if I take 3 and divide by 22.4133, I get a value for hydrogen gas equal to 0.134 moles, and that equals N. here's how I know that my units come out correctly. So you notice that I have atmosphere liters, and I'm dividing by atmospheres times liters over moles. Whenever we're dividing by a fraction, we actually have to multiply by the reciprocal. So this one up here is the same exact thing as multiplying by the reciprocal of the fraction. So now you notice I have atmospheres and liters on the top, atmospheres and liters on the bottom, so those go away. The only unit I'm left with is moles, so now I can see that my units are going to come out correctly. We'll have to follow the same procedure for oxygen gas. For oxygen gas, you should get an N value of 0.223 moles. Check and see if that's what you can get when we're working through those numbers. From our prompt, we do know that we were looking at the reaction of hydrogen gas and oxygen gas to form water. We know that we need to run this reaction because the problem asks us how much water vapor we're creating, but it only gives us information about hydrogen and oxygen gas, which means we're going to need to form a BCA table to make sure that that's okay. And that makes sure everything works out at the end. Looking at my BCA table, first thing we have to make sure is that our reaction is accurate and balanced. So my reaction right now currently is accurate. I have hydrogen gas reacting with oxygen gas and we're forming water, but it's not balanced. Notice I have 2 hydrogens on the left side, 2 on the right side, 2 oxygens on the left side, but only 1 on the right-hand side, which means that we're going to need to correct it by placing a coefficient of 2 in front of the water molecule. That gives me 4 hydrogens and 2 oxygens. So now oxygen is satisfied, but we only have 2 hydrogens on this side. So hydrogen will also need a coefficient of 2. Previously, we also found the mole values of both hydrogen gas and oxygen gas using the ideal gas law. So I can place those in the table now. We're going to need to determine which of these mole values is holding us back, which limits how much water we can actually make. So we'll have to do a couple of calculations. We'll have to check our options. So option 1 is that I'm going to turn all of my hydrogen gas into water. So my target term goes on top. I'm trying to determine how many moles of water we're creating. But in the process, I'm going to have to be exchanging all of my hydrogen for that. So I look at my reaction, I see that it's a 2-to-2 ratio. So for every 2 moles of hydrogen I put in, I'm going to get out 2 moles of water. So if I convert all of my hydrogen gas into water, I'm going to end up with 0.134 moles of water. So there's option number 1. Option number 2 is what happens if I convert all of my oxygen into water. So again, this tells me for every 1 mole of oxygen I put in, I'll get out 2 moles of water. So I can translate that down into our calculation here. And this says for every 1 mole of oxygen used, I'll produce 2 moles of water. So my other option is that I'll be creating 0.446 moles of water. I'm always going to pick the one that produces the least amount of product because it means that that's the reactant I'm going to run out of first. So that means that this is that reaction. This is that calculation that shows us that we only are going to produce 0.134 moles of water, which means that hydrogen is my limiting reactant, which means over the course of the reaction, I'm going to run out of hydrogen first. But I'll be producing 0.134 moles of water in the process. For completeness sake, we should also figure out how many moles of oxygen gas we're going to be using. So I'll start with my limiting reactant, and I'll see just how many moles of oxygen I'll need to make this process work. Looking at my calculation, I can see my reaction, I can see that for every 2 moles of hydrogen gas, I need 1 mole of oxygen gas. So running those numbers, I can see realistically that if I have 0.134 moles of hydrogen gas over the course of the reaction, I'm only going to be using 0.067 moles of oxygen gas. So I'm going to have some oxygen gas left over at the end. I'll have a grand total of 0.156 moles of oxygen gas left at the end. But the problem is only asking us about the water vapor. So that means I'm going to be creating 0.134 moles of water. And remember, the question asks us how many liters of water is that going to be? So how many liters of water vapor did we create? So now I have to use this value to figure out volume. So now we go all the way back to the ideal gas law. The problem stipulates that everything is occurring under standard temperature and pressure. I mean, standard conditions apply, which means that this is occurring at a pressure of 1 atmosphere and a temperature of 273 Kelvin. From our BCA table, we know we're also going to be producing 0.134 moles of water vapor. So now we have to take those and we have to plug them in and try and figure out, well, what volume is that going to occupy? Seeing all these variables together, it's a cue to me that we're going to need to be using the ideal gas law. Pressure for us is standard pressure, so that's 1 atmosphere. Volume is the thing we're looking for because that's what the problem asks us for in the beginning. It says what volume or how many liters of water vapor can be created. We know from our BCA table that we're creating 0.134 moles of water. R is a constant, always has a value of 0.0821 atmosphere liter over mole Kelvin. And our temperature is standard pressure, so 273 Kelvin. So we're going to do any of the math that we can do right away. So the first piece of math I can do is this entire right-hand side. I can take all those values and multiply them multiply by our gas constant, 0.0821, then I'll multiply that by 273, or our standard temperature. So I took a mole value and multiplied by this term, so I've got moles on So I took a mole value and I multiplied by this term, so I've got moles on the top and the bottom, so both of those are going to cancel when we're dealing with our units. I've got Kelvin on the top and Kelvin on the bottom, those go away. So whatever answer I got running these three numbers together should be in terms of atmospheres times liters. And the product of those three numbers gets me 3.003, and again, we decided our unit was atmosphere liter here. Now to get V all by itself, I have to divide both sides by 1 atmosphere. Notice I've got atmospheres on the top and on the bottom, so they're going to cancel out. And I get an answer of 3.003 liters. So over the course of this reaction, if I've got 5 liters of oxygen gas and 3 liters of hydrogen gas, I'll be producing 3 liters of water vapor. And that's kind of how we tie together the gas laws into our BCA tables and making sure that gases and our stoichiometry go together really nicely.